When it rains, stormwater runoff mobilizes pollutants from roads as well as sediments and agricultural waste from greenfield sites. Traditional gray engineered drainage systems, which include impermeable surfaces and underground pipes, carry the polluted surface water to a different location, keeping this issue out of sight and consequently out of mind for most people. Whether they are flushed down sewers or flow overland, the pollutants find their way into watercourses, lakes, and groundwater, putting the health of ecosystems and drinking water at risk. The contamination levels of most cities' water supply are disturbingly high and filled with toxic chemicals, heavy metals, and organic waste byproducts. To remediate this problem, harsh water treatments involving the use of acid treatment, including nitric hydrofluoric acid, hydrochloric orthophosphoric acid, hot sulfuric acid, and sodium dichromate chromic acid, and alkaline treatment using alkaline peroxide etch of titanium surfaces. Unfortunately, these chemical treatments invariably lead to the generation of a huge amount of sludge, and this ultimately leads to environmental degradation. In the 1980s, Paul Stamets, the leading expert in the field of mycology, proposed the revolutionizing yet unaccepted concept of mycofiltration. Mycofiltration is an innovative and environmentally sustainable technology which utilizes fungal mycelium networks to filter contaminated wastewater. Mycofiltration and mycoremediation techniques have only just started becoming more accepted as viable alternatives to harsh chemical treatments within the last 5 to 10 years. Many fungal species have proven viability in the use of mycofiltration, including the oyster mushroom, turkey tail, button mushroom, bluet mushroom, and the scaly inkcap mushroom. Certain species have shown to be more effective in filtrating specific types of contaminants and pollutants. A typical mycofilter comprises a burlap sac layered with a substrate of straw or wood chips and saprophytic mycelium. Once the mycelium grows throughout the sac as a network of filaments, they are placed in the body of water for decontamination. Mycofiltration has shown to efficiently remove microbial pathogens from stormwater, treat industrial effluent, remediate heavy metal contaminated drinking water sources, as well as remove nitrogen and phosphorus from agricultural runoff. Fungal mycelium networks do this by employing mechanisms such as biosorption, bioaccumulation, and biodegradation in the remediation of pollutants and xenobiotics. Biosorption is a passive process which occurs on the cell surface by ion exchange and reactions with carboxyl-amine hydroxyl functional groups and phosphate groups. Bioaccumulation is an active metabolism dependent process involving the transport of pollutants into the cells and partitioning into intracellular components. The biodegradation mechanism involves the degradation of non-polymeric recalcitrant pollutants into simpler elements by extracellular enzymes. Several species of fungi have been studied and have demonstrated an exceptional ability in the uptake and removal of metals and other pollutants from waste and/or runoff water. These fungal species can be either in live form or in dried biomass and have effective bioabsorption potential for metals such as copper, zinc, iron, and manganese. These fungi hold the ability to transform pharmaceutical compounds as well as break down pesticides. Fungi have proven to be an effective, cheap, and environmentally sustainable way of removing various pollutants that contaminate wastewater and the environment. With the ever-growing threat of environmental degradation, there is an immediate need to solve the countless existing issues involving contamination and pollution. Mycofiltration provides a safe and effective remediation technique for water treatment. Fungi and the use of mycoremediation may hold the key to solving the environmental crisis we are in today. Thank you.